Hello everybody, today I'm back with another video, and today I'm going to be covering improper integrals, which is a topic in Unit 6 of AP Calculus BC. It is a BC only topic, and it is not covered in AB, so if you're in AB you don't really need to watch this, but if you're in BC, I highly recommend that you do if you don't know what improper integrals are. And if you don't know, well, I'm going to show it to you right now. So let's say we have the function y is equal to f of x is equal to 1 over x. So the function f of x is equal to 1 over x. That's the main thing. So, and I graphed it right here. So this is just f of x, y, if you want to call it, either way. And what I want to find out is the integral from 1 to infinity. Now you might be wondering, well, how do we go about finding that? So I'm going to show you right now. What we're going to do is we're going to graph. We're not going to graph. We're going to write the integral sign. You probably know this by now. You've been doing Unit 6 stuff, so I'd assume. Then we have 1 to infinity, because, and I'll show you why. So I want to find out from basically all the area underneath the curve that goes, that's from x is equal to 1. So we have x is equal to 1 as our starting bound. I like to call it starting bound. And we have infinity, because this function, it goes all the way to infinity. It never reaches 0. I want to find out all the area underneath it, and so I want to find out from 1 to infinity. Well, I'll show you guys how to actually do this in just a second. So we have 1 over infinity to our function f of x, but I'm just going to write 1 over x, and of course we need to write dx. Alright, so how do we go about solving this? So I'm sure you guys can anti-differentiate 1 over x pretty well, and that just turns out to the natural log of x, usually with the absolute value inside. And so once you have that, you can kind of solve it like you would. So when you actually find the antiderivative, what you do is you can put it in here. You have, and then what we're going to do, before I put an infinity here, I'm actually going to put in n. And what I'm going to do is I'm going to put the limit as n approaches infinity. So this is how we solve an improper integral. Instead of solving the integral with infinity, we instead replace infinity with a variable, typically denoted as n, though you can actually use whatever you want. And then we put the limit of that as n approaches infinity. And so we would have done this the step before, but I decided to do it here so we could actually see the original integral still. So we have the natural log of 1, because let's solve that because that's a bit easier to solve. And the natural log of 1, what is that going to be? That is going to be 0. And so what we can do is we can find out if, so I'll take this to the next line, is equal to the limit as n approaches infinity, and that is going to be the natural log of n minus 0, and minus 0 obviously doesn't do anything. So once we have this, what can we do with it? So if you guys know, as the natural log of n approaches infinity, it gets bigger and bigger. It keeps on getting bigger. It doesn't stop. So what'll happen is it keeps on going to infinity. Ln of n will keep on going to infinity, and since we're seeing what happens as this approaches infinity, what happens as the limit as n approaches infinity gets bigger for the function of the natural log of n. That's basically what I'm saying, and it gets bigger and bigger. The graph of the natural log of n looks something like this, and oh, sorry, not exactly how I want to draw it. It looks something like this, and it keeps on going bigger and bigger. It keeps on growing bigger and bigger with no, and it does grow slower, but it doesn't have a upper bound, so to speak. So once we have that, we can use this to say, since this does go to infinity, you can say that this is equal to infinity, meaning that this does not exist. And what we can also say is another thing. So you can also say dne for does not exist. You can also say on top of this that it is divergent. And this, you can say the integral is divergent. That's basically what you can say. And if this were to come up with a certain value, try this on your own with 1 over x squared. See if you can get a different value. And I'm pretty sure that you will. You'll get a set value. You won't get infinity like we did here. We got infinity here, but if you try it with 1 over x squared instead of 1 over x like I did in this example, then you will get a specific value. Once you have a specific value like that, what that means is that the integral in that case is convergent. And this may not seem like anything important. It might be asked in your calculus class, like, is this integral divergent or convergent? But this will become more important when you get to series and sequences, and specifically the integral test. You will use this divergent and convergent topic pretty often. It's kind of the main thing there. And yeah, so this is kind of like a little bit of exposure to that, and you'll see how it uses an improper integral to actually solve, to actually demonstrate how the integral test works. So I hope this helped you understand what an improper integral is. I gave a little bit of an introduction to what it does in terms of the integral test, but the integral test is not relevant for this video. Oh, it kind of is to an extent, but yeah, so I hope you guys did find this video helpful. If you did, please leave a like down below. Leave some feedback. I think I was a bit more nervous during this video because it's kind of a newer topic. This is a topic that I covered a bit more recently. Some of the other topics that I covered are like a bit more, they're a bit, I've worked with them a lot more, improper integrals, not really as much. But yeah, I hope you guys did find this helpful. If you did, please leave a like, as I said earlier, and be sure to subscribe as well. Notifications, keep them on if you do want notifications whenever I upload a new video. And anyways, guys, thank you guys so much for watching once again. And be sure to see you in the next video, and I'm running out of storage space.